Okay, so let's start the session formally. Good evening, everyone. Welcome to week 6 of the problem solving session for Analog Circuits course. I am D. Sharda Devi, a PMRF fellow from IIT Gandhinagar. So, in today's session, we'll be discussing about filters. Like, until now, we have seen amplifiers. So, filters are another one of the most important circuits in analog circuits domain. So, when we talk about filter, the idea of filter is same as in layman terms. We know what is the idea of filter, or in general what is filter basically separates something out, right? When we have, let's say, in our real life domain, we have filters, we use filters. So well, many people must be tea enthusiasts, right? So tea enthusiasts have to sieve out their tea leaves after the tea is made. So that is filtering process. So filtering, what it does, it selectively removes certain amount of certain stuff out of the total that we have. Similarly, in our analog circuits, we have filters. These particular circuits are used for selection of signals, and they perform selection in the frequency domain. So the idea is filters are actually frequency selective circuits. These are frequency selective circuits. So what they do is they allow certain amount of frequencies, certain number of frequencies to pass through uh, the circuit, whereas they block the other frequencies. And depending on this frequency selective, like based on this frequency selective process, we have different kinds of filters. Like if we talk about basic types of filters, so we have, like, for example, low pass filter, high pass filter, band pass filter, band stop filter, and there is another filter called all pass filter. So we'll go through these filters one by one in a brief, and then we will move into our problems, which are all based on filters for today. So starting with the first and the basic filter that we have is a low pass filter. So low pass filter, as the name suggests, it passes the lower frequencies. If we talk about the frequency response of this particular filter, so the frequency response of a low pass filter looks like this, where we say this is the cutoff frequency. This is gain, frequency. This is FC, where FC is cutoff frequency. This is the same frequency that we have been observing, uh, cutoff frequency, or we can also call it as 3 dB frequency. Yes,
Madam, excuse me.
yes.
Is it high pass or low pass?
Oh, sorry, low pass, right? It passes low, and it is opposite. So it passes low and it blocks high frequencies. So this is the behavior. Yes. Thank you for pointing out. Sometimes we have something in mind, but we draw something else. Yeah, so this is the profile. It passes the low pass. So when we say it passes a certain frequency, the idea is that the gain in those frequency ranges is fixed. So if we have a certain range of, we say that this is the pass band of my filter, That means in that particular range of frequencies, my gain should remain fixed. So for all the frequencies, I should obtain equal, like same amount of gain. That is the idea for the passband. So this is called passband. All the filters will have a passband and the stop band. Okay, and the steepness of the filter, it basically depends on the order of the filter. So this is increasing order. The higher order of the filter, higher the order of the filter, the steeper the curve would be. And ideally, if I talk about, if I want a low pass filter, the ideal behavior should look somewhat like this. My ideal behavior should look like this. So practically, we try to obtain this ideal behavior by increasing the order of the frequency or order of the filter. And when we say we are trying to increase the order of the filter, so how do we increase the order of the filter? So we have seen that in our Bode plot analysis, when there is a single pole that we obtain, let's say at FC we have a pole, then the slope of the curve drops by minus 20 dB per decade, right? So let's say if this is minus 20 dB per decade, then to make the slope steeper, I need to add more poles at the same point, right? So say this could be minus 40 dB per decade. And similarly, this could be say minus 60 dB per decade. So the more the poles I add at the given position, the steeper my slope will get and it will approach the ideal behavior. But we can also understand that as we are increasing the number of poles, we are also introducing our components. So pole, we know a pole is defined by what? So a capacitor and resistor, right? As simple as a capacitor and resistor can give us a pole. So the more poles we want, the more components we have to introduce in our circuit, correct? So it increases the bulkiness of our circuit. So our circuit becomes bulkier. So as we try to approach the ideal behavior, our circuits become heavy and bulky. Okay. So yeah, now if I ask you, say, I want this kind of behavior where it stops after some time and yeah. So if this is the behavior that I want, so in the transfer function, like looking at this pole zero, like this transfer frequency response, can you tell me how many poles or zeros are required for designing a low pass filter? Like simplest low pass filter, how many poles and zeros are required to design this? See, how is the response? We have a DC component, like we had a constant gain. So if there is a constant gain, that means we don't have any pole or zero at the origin, correct? Since we are starting with a constant gain. After that, we have a cutoff frequency and our gain drops with a slope. So the minimum number of poles or zeros that I require. So first of all, for obtaining this kind of behavior, what do I need? Do I need a pole or a zero? I had a constant gain. Now my slope comes down. So what do I need? Do I need a pole or a zero in this case? Yes, anybody? What do we need, a pole or a zero to get this behavior?
One pole.
Pole, right? So I can design a low pass filter by as simple as having a single pole. So one pole can give me a low pass filter. In short, we call it LPF. Okay. So a single pole system can be used as low pass filter, right? We can also like have a zero after the pole just to stop the fall. So if my transfer function, like if I don't have a zero, my transfer function or the gain will start to reduce continuously, right? It will go down infinitely. But since those frequency ranges are not of my concern, so I need not to care about it. So I can design a low pass filter by as simple as using a single pole. But if say I want to stop this like fall of my gain, and I want to restrict my like stop band gain to a certain level. So since this is my stop band, I want to have a certain stop band gain in my system, so I can introduce a single zero as well. But the simplest like low pass filter can be designed using a single pole system. Okay, so this is all about low pass filter. Now then, after low pass filter, we have high pass filter. Now high pass filter, as the name suggests, it will pass higher frequencies and block the lower frequencies. So this passes higher frequencies. And its frequency response is just opposite to that of low pass filter. So here we will have higher, at higher frequencies our gain stays constant, and then we see a fall. Okay, so this is FC, F and gain, right? Okay. So now if I want to design this low high pass filter, what type of transfer function I would need? Like how many poles and zeros I would need at minimum to design a high pass filter? How many poles and zeros I would need? Let's say we are starting at certain level. This is again my stop band. This is my pass band. So I have a stop band. It had some gain, constant gain, right? And then say here my gain starts increasing. So I would definitely need 1 0 since my gain is increasing. And now at FC, I have to make my gain constant. To obtain that gain, I need one pole. Correct? So, yes. So for a high pass filter, what is important is we need 1 0 and one pole. So minimum 1 0 and one pole are required to design a high pass filter. As simple as a very basic high pass filter would need one pole and 1 0. Okay, and here also, if we try to reach like to make an ideal high pass filter, we need to increase the order of the filter. And it is true for all the filters. Like as you want to have an ideal behavior from the filter, you need to increase the orders. And as you start increasing the orders, your system becomes bulkier. So that is true for all the cases. Okay, so now this is all about the behaviors, right? Now, if we talk about how will the circuit look like, right? So a simple low pass high pass filter can be designed as simple as using an RC circuit. Simply by using a RC circuit, you can design a low pass and a high pass filter. Okay. So now maybe we can analyze the RC network, and this analogy can be used for other type of filter designs as well, which can be designed using op amps and other circuits too. So now, see here, what is happening is, first of all, we know that filters are frequency selective networks. That means whatever signals or inputs that we will give, we have to change their frequencies to observe what are the frequencies for which your circuit gives you like a proper output, and what are the frequencies for which your circuit blocks those frequencies and you don't get good output. So that is the basic idea. Now, if I talk about, say, circuit A, so in circuit A, if we see there is a resistor and a capacitor in series, but we are observing our output across the capacitor. Now in B, what I have done is I have simply interchanged my capacitor and resistive positions, right? We know few behaviors about capacitors, because capacitor is the only component which is frequency sensitive. So capacitor is a component that is frequency sensitive. Now for capacitor, we know for low frequencies, we know that Xc is 1 upon omega c. So as omega is low, as omega reduces, Xc starts to increase. And as omega increases, Xc starts to reduce. So say omega equal to 0. Omega equal to 0 is ideally the DC condition. So in DC condition, my Xc will be infinite. Similarly, omega equal to infinite, which is a very high frequency signal. So for high frequency condition, my Xc becomes 0. So if I say Xc is infinite, if my resistance is infinite, so basically the condition is of open circuit, correct? And for Xc equal to 0, the condition is that of a short circuit, right? This is something we all know. Now, how to analyze our circuit based on this? That's the idea. So, see, here in case A, when we have A, now let us analyze this A for two different conditions. Circuit A for low frequency and high frequency conditions. So first of all, in low frequencies, that is F equal to say 0. Okay, the DC condition. We know that in DC condition, capacitor is like the capacitor becomes open circuit. So how do my resultant circuit look like? So it will look like this, somewhat like this. You will have V in. Now here if I ask you, what would I get in output? What is my V out in this case? If my capacitor is open circuit, what is the V out that I'll observe?
Uh, Madam, you will get V out something less than Vi,
No,
because
it will be completely VI. So because here it is open circuit situation, right? So there won't be any current flow through the resistor, so there is no drop across the resistor. And
Okay.
since there is no drop across the resistor, ideally what we would get is V out equal to Vn, right?
Okay.
So this is the condition for low frequencies. Now, what will happen in high frequency case? So when we have high frequencies, that is Fc equal to infinite, in that case, we know that our capacitor becomes short circuit, correct? So now, if we have short circuit, what is the output that we get? If we have a short circuit, what is the voltage drop we get across our, like, a short circuit system or a short circuit path? The output is 0, correct? If we have a short circuit path, the output in that path would be 0, right? Because there won't be any potential difference. Sorry. So it's a very high. So the idea was in low frequencies, we are considering the frequency, like ideally to get a value, we are considering frequency to be 0. In high frequency, we are considering ideally the situation to be of frequency that is equal to infinite, just for simplification of calculations and for understanding. And we know that Xc is 1 by omega c. So whatever is the omega, opposite would be the behavior of the impedance or reactance provided by the capacitor, right? So that is the reason that in high frequencies, our capacitor becomes short circuit, and in low frequencies the capacitor becomes open circuit. So now we have seen this behavior. Now if say I want to like intuitively plot my frequency response based on these two analysis, so how would my frequency response look like? So we observed that this is gain, and since V out equal to V in, so gain is 1 in this particular case, right? Gain is 1. So since the gain is 1, we have seen that in lower frequencies, the gain is 1. So let's say until some frequency, the gain will remain constant and it will be 1. At higher frequency, so this is 1 and this value is, say, here I am showing it to be 0. Okay. So if this is my 0, we know that at very high frequencies, we have got our output to be 0. And there must be some transition, right, between 1 and 0. So that transition would come like this. And if I ask you what type of filter behavior is this? So what type of filter behavior is this based on my frequency response?
Low frequency.
Yes. So it is a low pass filter, correct?
Pass filter.
So using a resistor and a capacitor, we have got a low pass filter, right? Now, in the similar way, if say I analyze so I drew two circuits, right? One was a resistor followed by a capacitor. Now, what if I draw a capacitor followed by a resistor circuit? And if we analyze this circuit, which is B, so let's see how the behavior changes. We have only interchanged the positions, right? We didn't do anything, like nothing much has been done. It's just the positions have been interchanged. Now, here again, we will have two conditions, that of high frequency and low frequency, as we did earlier. So yeah. So let's start with low frequency condition again. Capacitor behaves the similar way, and this is now, if my frequency is 0 in low frequency, what we discussed that in low frequency, the capacitor becomes open circuit, right? So if my capacitor becomes open circuit, and here I have a resistor R, this is V out. So if this is the situation, what is my V out then? So there is no path between input and output voltage, correct? Since it is an open circuit means there is a breakdown over there. So if there is no path, then V out would be 0, correct? And in the similar way, if I have a high frequency signal going, then my capacitor would be short circuited, and I'll have this resistor, and the voltage across the resistor is my output. So in this case, we can clearly see there is a short circuit path between V in and V out. So because of this short circuit path, my output voltage becomes equal to input voltage, right? Now, from the behavior itself, you can observe that the behaviors have just turned opposite to each other from the previous case. So in the previous case, for lower frequencies, we had gain of 1, and for higher frequencies, the gain becomes 0, or the output basically becomes 0. In this case, we see that for low frequencies, our output is 0. Say this is the 0 value. So for low frequencies, the output is 0, and for high frequencies, the output is 1, if this is gain. And then we will connect these two, and this is the behavior of a high pass filter, right? So from here, we can clearly observe that a first order low pass or high pass filter can be designed using a simple single capacitor and resistor. Okay? And we have already observed that for a low pass filter, we would only need a single pole, nothing much is required. And for high pass filter, we would need a pole followed by a 0 to get the behavior of a high pass filter. Okay, so we have analyzed low pass filter, high pass filter. We have also seen the basic circuit. These type of circuits now can be followed by an amplifier. So op-amp based low pass and high pass filter can also be designed. And in op-amp, again, the filters can be for inverting configuration as well as non-inverting configurations. Both are allowed and both are available. So this is all about low pass and high pass filters. Now if we move ahead, so till now we have seen that low pass and high pass filter. So third type of filter is, say, band pass filter. Okay, band pass filter. So when I say a band pass filter, as the name suggests, it will pass a band of frequencies. Okay, passes a band of frequencies. That means it would block the remaining other frequencies. So if we talk about the frequency response, how it looks like for a band pass filter, so it is gain versus frequency. This looks somewhat like this. Okay, so this is the pass band. These are like low and high cutoff frequencies. This is the bandwidth. Okay, this is the bandwidth, and again these are stop bands. Now, if I ask you how many poles and zeros are required for this band pass behavior, so can you tell me how many poles and zeros are required just by looking at this like frequency response for a band pass filter? How many poles and zeros we need? Yes. How many? Okay, tell me at this point, what would you need? So, like until here, it was a constant value. So, say some value, some DC gain you had. Now, after that, you encountered either a pole or zero at this point, A. Yes, at A, what would you encounter? A pole or a zero? Yes. At A, is it a pole or a zero present? It is a zero, right? It is a zero at A, correct? Since my gain is slowly increasing, that means I have encountered a zero, right? Now at B point, my increasing gain has stopped. So that means a pole has been encountered to counter the effect of a zero, right? Now again at C, the constant gain has started reducing. So if the constant gain has started reducing, that means again I have encountered another pole. And at D point, since that gain has stopped, so it is a zero again. So it's either you can say 102 pole system, considering that the left rightmost stop bands are not required, or else you can say 2 pole 20 system, right? So if I talk about the orders, so for first order band pass filter, you would need 2 poles and 1 or 2 zeros. And we have discussed this earlier that depending on the power of the denominator, we call it the order of transfer function. So since I have 2 poles, that means it would be S square. So the order is 2. But if I talk about a first order band pass filter, that means a first order band pass filter would be a second order transfer function with 2 poles and one, at least 1 zero. Getting my point? So band pass filter is already a second order system. A first order band pass filter. So if I say, okay, so let's see how can you design this band pass filter. Okay, that is interesting. We want this kind of profile, right? We want a profile where, so can you see some similarity from low pass and high pass filters in this particular low pass behavior or a band pass behavior?
Yes, madam. We can
Yes,
cascade.
right?
We can cascade these two high pass low pass. Cascade.
Yes, we can cascade the two to get this behavior. Now, how that will happen? See, first of all, to obtain this A to B region, A to B region is similar to that of a high pass filter profile, right? So it's like this, then we have a slope and then this. So this is my high pass filter, correct? Now, if I say my FH and then D, that portion, it is similar to that of a low pass filter, correct? So if I have to draw, so how will a low pass profile look like? So it is like this, and then we will have the slope and then this. So this is my low pass profile. And what I want the resultant behavior should be like this. So now this is my band pass filter. So see, from here we can clearly observe that I can use one low pass filter one high pass filter to get a behavior of my band pass filter, correct? So now tell me, which filter, in which sequence would you use this low pass and high pass filter to get this band pass filter? Will you use them in parallel or one after another? If one after another, will you use a low pass filter first, then a high pass filter, or will you use a high pass filter first, then a low pass filter? Yes.
Low pass followed by high pass.
Okay, so somebody said low pass filter followed by a high pass filter, right? Now see, let's analyze how the things will look like, okay? First, you are going for a low pass filter. Okay, so you had all the frequency ranges. Now you have passed it through low pass filter. So after low pass filtering, how will my transfer function or the behavior look like? It will look like this. So this is the result of low pass filtering after LPF. Correct? Now after this, I'm going for a high pass filter. So if I go for a high pass filter, now in the resultant, so earlier, so we had all the frequencies. Out of them, we have selected some frequencies through low pass filtering, and then we are going for after high pass filtering. After high pass filtering, we have to be very careful about the cutoff frequencies. Okay, so F1. If I consider my cutoff frequency of high pass filter greater than F1, so I would not get any output, right? If say the cutoff frequency is F2 for my high pass filter, now it can have two conditions. One is, so here we can have two conditions, F2 greater than F1, F2 less than F1. So if F2 is greater than F1 and say F2 falls somewhere here, F2 dash, and say here it is F2 double dash, okay? So F2 dash, then how will my output look like? So I would get an output somewhat like this, right? So this is from F2 dash. So this is the only output that I would get, right? But if I have F2 double dash, that is the cutoff frequency of my high pass filter. So how it would look like? And before that also it will be like this. Okay. And in this particular case, how it will look like? So this is F2 double dash. Here somewhere it was F1. So I'll get this gain, constant gain. Here this will drop and again this will drop. So this is my pass band. This is stop band. So here we have observed, right? So it is very important to first of all understand that the cutoff frequencies of both the filters which I'm going to use to create a third filter, the cutoff frequencies are very important to understand, because based on the values of the cutoff frequencies, you will get the profile that you want, right? So this was one condition where we have used like a low pass filter followed by a high pass filter, right? What if I use a high pass filter first, then a low pass filter? What do you think? What would happen? say I use a high pass filter followed by a low pass filter. Can I do that? What is your opinion on that? Can I use a high pass filter followed by low pass filter? Yes?
Madam, we can use, but it will not be a band pass filter.
If I use a high pass filter followed by a low pass filter, it will not be a band pass filter. Okay, let us analyze, right? So I had all the frequencies in my hand. I'm passing it through a high pass filter, okay? So here, after passing it through a high pass filter, this is the profile that we would get. Say this is the profile that we are getting after passing through high pass filter. This frequency is F1. Now, again, if I pass the same signal through my low pass filter, if I pass the same signal through my low pass filter, so what is the caution that I have to keep in mind? Yes. What is it that I need to keep in mind? Or is it impossible to get this behavior of, uh, or is it impossible to get a behavior of band pass filter by this method? Yes. Anyone? What do you think?
We have to set the limits of cutoff frequencies, lower cutoff frequency of high pass filter and higher cutoff frequency of low pass filter.
Yes. So here also we can get the same behavior of band pass filter. The only thing that we have to again keep in mind, which is very important, is the cutoff frequencies again, right? So here my low pass filter has a frequency of F1. So this will act as my lower cutoff frequency. So my for high pass filter, the frequency F1, the cutoff frequency will act as a lower cutoff frequency. So the low pass filter should have a cutoff frequency higher than F2, higher than F1, that is F2, such that I can recreate this band pass behavior. Okay. So this is only possible when I have F2, this is F1. So F2 greater than F1. Here the cutoff frequency is F2, here the cutoff frequency is F1. So we can go by in either ways, that is high pass followed by a low pass, you would get a band pass filter. Low pass followed by a high pass also, you would get a band pass filter. But the only thing that we need to keep in mind is how we are setting our cutoff frequencies. In a band pass filter, the cutoff frequency of your high pass filter is lower than the cutoff frequency of your low pass filter. Is this clear to everyone?
Okay, madam. Okay.
Okay, right? Okay. So we are done with low pass filter, high pass filter, band pass filter. The fourth category of filters is a band stop filter. Again, as the name suggests, it stops a band of frequencies. And if we talk about the profile, so it is just the opposite to that of our band pass filters. Okay. So the band stop filter profile looks like this. Okay. So here these are pass bands. And this is stop band. right? Now again, if I ask you how many poles and zeros are here,
two poles, two zeros, madam.
here again 2 pole 2 zeros. So we had one pole here, a zero, and a pole. So if you see, the behavior is also opposite. Here it was pole zero, zero pole zero for band pass filter. In band stop filter, you need pole zero zero pole. Okay, and again this is the bandwidth. Bandwidth of our band stop range. Now, my question is, if I want to design this band stop filter, how would I design? Using similar low pass, high pass filters. Yeah, how would you design this band stop filter? Anyone?
Madam, low pass cutoff frequency should be higher.
Okay, so I'll use one low pass filter with say FL greater than FH. That is what you're saying. So what is the sequence in which you will use the filters for band stop filter? BSF, okay? BSF, yes. So for BSF, how would you design it? So first you will use a low pass filter. Then followed by a high pass filter.
Followed by high pass filter.
Okay, if you have low pass filter followed by a high pass filter, would you get this behavior? What do you think? Would you get this behavior? Let us analyze. See, in the beginning, you had all the frequencies, correct? You passed it through a low pass filter, right? So after low pass filter, how it will look like? We will see this behavior, this and this has gone down. This is our pass band, right? But I want this second pass band again, right? How will I get that by using a high pass filter? In this particular condition, so 1, 2. When you have 2 and you want a behavior like this, can you get it using a high pass filter? How will you get this pass band? Will you
By
get it?
selecting the cutoff frequency of high pass filter higher.
No, if you select the cutoff frequency higher, then is there any signal left? So if you say this is your FL, okay, you're saying you want your FH should be greater than FL, okay. So if my FH is greater than FL and I start drawing, how it will look like, say FH falls somewhere here. And this is your FH position. So after FH, there is nothing left. And before FH also, there is nothing left. This is what a high pass filter does, right? Before the cutoff frequency, everything will be gone. And after the cutoff frequency, the things will remain as it is, correct? Am I right? So, everyone, do you understand this behavior? Like how we transition from 1 to 2 to 3? Any doubts in this? Or anything you feel which has gone wrong from 1 to 2 to 3? Anything that has gone wrong? Do you think anything is wrong in this? Any comments, anything? Okay, how many of you think that the analysis that I have done from 1 to 2 to 3 in this particular graph is correct? Raise your hands. Those who think the analysis is correct, please raise your hands. Okay. Now, those who think the analysis is incorrect, that the analysis is wrong, please raise your hands. Okay. So, no comments. So, you don't know whether the analysis is right or wrong. You don't understand. Do you want me to go through this once again?
Yeah, yes, madam. Please.
Okay. Right. So you should have told me, no? You didn't understand, you want me to go through this again. See, when, let us understand from the basics, very basics, okay? You have all range of frequencies in your signal. This is your input, okay? You're passing it through a low pass filter. All right? Now, when you pass it through a low pass filter, what do you expect in the output? That only lower frequency signals should remain in the output and higher frequency signals should be eliminated. Correct? Yes or no?
Yes, ma'am. Yes.
So, how will my profile look like? So, I'll see my lower frequency signals with certain amount of gain, and then my higher frequency signals will be eliminated, almost say zero gain. Correct? That is the idea. And where your curve starts, or you will encounter a pole, we call it a cutoff frequency. This would be the cutoff frequency for a low pass filter, right? Now, for the same signal, when we use a high pass filter, okay, you have all the frequencies. Now you are passing it through high pass filter. So what is the idea of high pass filter? That it will allow your high frequency signals to pass as it is with a certain amount of gain, or let's say unit gain, and your lower frequencies will be eliminated. That means the gain that you would observe for lower frequencies would be zero, and your pass band would have certain constant gain. Correct? Am I right?
Yes, madam.
No doubts in this, right? No doubts in low pass and high pass working, right? How we transition from input to output. No doubts, right? Okay. Now, we are saying that we want to design a band stop filter. The suggestion was that let's use a low pass filter followed by a high pass filter. Okay. So, for that analysis, again, see. This is the analysis for low pass filter. I'm using it as it is. Okay. So here what we did is, we have all the signals, we passed it through low pass filter, we got this profile, right? Then what we are saying, we will pass it through a high pass filter, correct? Now high pass filter should be such that the cutoff frequency of low pass filter should be smaller, or high pass filter should be larger, right? So if this is FC or say FL, the idea is FH should be greater than FL, correct? This is what you all said. Am I right? Am I right or wrong? This is what
Yes.
you expected, right? So now let's say my FH is here. So FH is greater than FL, right? Now, what we said, in high pass filter, after the cutoff frequency, whatever is there, it will pass as it is. The frequencies higher than cutoff frequency will pass as it is. The frequencies lower than cutoff frequencies will be eliminated, correct? No doubts in that, right? Yes. No doubts in that, right? Whatever I said right now. In high pass filtering, what will happen is the frequencies greater than the cutoff frequency will be passed, and the frequencies less than cutoff frequencies will be eliminated, right? So now, in this case, when you are passing this to your high pass filter, what it will see, it sees at FH it has certain value, say X. Okay. So the signal X, and after that it will follow the curve as it is, right? And below FL it will start to eliminate. So it will slowly diminish and go to 0. So this comes from the order of the filter, right? This behavior we discussed, it comes from the order of the filter, correct? The higher the order, the steeper the slope you would get. And this part is same as that of your this particular portion is same as that of the curve that you gave in input. This particular region. This transfers to your output. So these two are same. Is this clear? Yes, somebody raised their hand. What is the doubt? Yes, who raised their hands? What is the doubt? So is this analysis clear? Low pass filtering followed by high pass filtering. Any doubts in this? Can you unmute yourself and ask? It will be easier for others also to listen to you and understand the problem. Yes, who raised their hands? I guess it was Sai Kumar. What was the doubt? Yes, what was the doubt? So did you people understand this? Any doubt in the analysis? Yes. Any doubt in this analysis? Yes, no, did you understand? Didn't you understand? What is the situation? I am unable to understand. Did you get it? How we first low pass filtered it, then high pass filtered the signal, and what we found out is for band stop filtering, low pass filter followed by high pass filter does not work, right? So this suggestion does not work. Is this clear from the analysis?
Yes, madam. Yes.
Okay. So anything else that you can think of? What else?
High pass followed by low pass.
Oh, you want to do it other way around?
Yeah.
ठीक है. So this is suggestion 1. Now the suggestion 2 is for BSF, you want me to do high pass filter followed by a low pass filter, correct? So let's quickly do this. So this is frequency, high pass filter, how does the profile for a high pass filter looks like this, correct? Okay. How do you want to keep the profiles, like frequency profiles, cutoff frequencies? How do you want to distribute them for high pass and low pass filter?
For high pass filter, cutoff frequency higher than low pass.
For high pass filter, cutoff frequency higher than low pass.
Low pass cutoff frequency.
Okay, so this is your FH. What do you want me to do? FL should be greater than, less than. For low pass filter, what?
FH should be greater than FL.
FH should be greater than FL. This is what you want?
Yeah.
Okay. So if FL is less than FH, say here somewhere your FL would come, right? Correct? So here it is FL, here it would be say FH. Now again, we know for low pass filtering, whatever frequencies are less than FL, the signal will pass as it is. Correct? So before FL, whatever is the signal, it will pass as it is. Right? After FL, your frequencies will be eliminated. So you will see some slope depending on the order of the filter, and then your signal will be eliminated. Right? So here again, if I have to highlight, so this is same as this. So again, do you see the behavior of a band stop filter? Yes. Similar analysis, right? It's just that first you did low pass filtering, the high pass filtering, and followed by low pass filtering. Do you see band stop filtering behavior?
No, madam.
No, right? So this also does not work, right? What else can be done? See, now here, let me suggest you something. That is suggestion 3, right? How is the transfer function or my frequency response for band stop filter looking like? It is like first it passes a signal, then it stops certain frequencies. After that, it again passes some frequencies, right? So separately, I see this is low pass filter behavior, this is high pass filter behavior, right? What we already observed is that using one filter followed by another is not working here. What if I tell you that let's use both the filters and use an adder? So if I tell you that let's use a low pass filter and a high pass filter both in parallel, okay? So to them the input will be full frequency ranges to both of them. And then what we will do is we would use an adder, and the resultant output that we would get is that of a band stop filter. Do you think this will work? Yes. Will this work? See, here the behavior would be like this. Here the behavior would be somewhat like this. The only condition I want to consider here is FL, this is FH. FH is greater than FL. So what I get is FL here, FH here. So this works, right? Any doubt in suggestion 3? So what we did is we are using a low pass filter and a high pass filter in parallel. And then we are adding or summing their outputs together to get the band stop behavior. Is this clear?
Yes, clear, madam. Clear.
Yes. So this is actually how you design a band stop filter.
Ma'am, one question.
Yes.
Can these band stop and band reject filters
Yeah.
can be designed using active passive components?
Using passive components. I mean, you can do, but the thing is you would need a summer.
Okay.
Summer is required, right?
Okay.
So somehow, if you have a summer, you can use passive low pass filter. We discussed passive low pass filter earlier, right? Passive low pass filter and passive high pass filter. We can use that, and if we have a summer, we can pass through the outputs and we'll get the band stop or band reject behaviors.
Okay, madam.
Yeah. So this is also, as well pointed out, this is also known as band reject filters also. And if you make this band rejected band, so we have a band, right, for band rejection. If this band rejection is made very narrow, say if you can eliminate a single frequency, then that particular filter, it is also a band reject filter, but rather than rejecting a band, what you are rejecting is a single frequency. Then that filter is known as notch filter. Okay? So notch filter is nothing but a band reject filter or band stop filter only. Notch filter, it rejects a single frequency. A single frequency. Yeah, to be to be ideal. So if we talk about an ideal notch filter, it should reject a single frequency. So where can we use this notch filter? So we all know that all our systems have this supply has a 50 hertz frequency, right? In India, we have a 50 hertz frequency supply. And say you are designing some circuit and you want to eliminate the noise that comes from the supply, or you simply want to eliminate the frequency that is not your signal, right? That is not an input. It is a supplies frequency. So you don't want the hindrance because of that supply frequency. You want to eliminate it. So there you can use a 50 hertz notch filter. So 50 hertz notch filter will eliminate that only 50 hertz component and it will pass all remaining components. So that is a notch filter for you. Okay. And there are special designs and special cares taken to create these notch filters so that they eliminate only a single frequency. So maybe if time permits, we might look into it. But yeah, they have a special design. So so you can look up online or in books also. You will find special designs for notch filter. All right. So till now we have done high pass, low pass, band stop, band pass filters. There is one more basic a filter which is there. We call it a fifth filter, right? All pass filter. All pass filter. So as the name again suggests, it passes all the frequencies. So the idea is, if I have this kind of frequency response, I pass it through a all pass filter, APF. In output, what I would see is the same response again. So then the question arises, what is the use of this filter, right? We said that filter is a frequency selective network. It selects some frequencies, or it rejects some frequencies. But in all pass filter, we are saying that it passes through all the frequencies. Then what is the use of it? Genuine question, correct? What is the use of an all pass filter? So this all pass filter basically introduces, or it can be used to introduce, phase shift. These filters are used to introduce phase shift between input and output. So for all pass filter, the difference that you would observe is not in the magnitude Bode plot or magnitude frequency response. Rather, you would see the difference in the phase response. And if we talk in the real-time perspective or real-life perspective, so introducing phase difference or phase shift basically means introducing delay in time domain. So if you want to delay a signal by certain amount, what you would do is you would use an all pass filter. So introduce a delay. Okay? Because when we have sequential circuits, the timing is very important. Like two signals have to come at a certain given time only, then only the output that you will get would be a good output or a correct output. If timing is a little off, the output that you would get might not be a correct output. That's why timing is very important for the signals. So to maintain those timings, sometimes you might require to delay certain signals so that you can get correct outputs. And when you have such situations, what you do is you use these all pass filters. Is this clear to everyone?
Yes, madam.
Okay. So with this, we are done with all basic 5 types of filters that we have. Now, based on these filters, you can start increasing the orders. You can design these filters as I have shown the example of a passive filter, where we have used a resistor and a capacitor. You can design these filters using active components, like using op amps and all. And you can again get low pass filters, high pass filters. All right. So that is the idea. Now let's come to problems that I have decided for today. So this is the first problem. Okay. So here a transfer function is given to us. The idea is just by looking at the form of the transfer function, determine the type of filter that can be used, that can be analyzed through this particular transfer function. So we have transfer function. By just looking at the transfer function, how to decide whether the transfer function is for a low pass filter, high pass filter, band stop, or band pass filter, right? So just by looking at the transfer function, first thing that we can do is tell me how many number of poles and zeros are available. By looking at the transfer function, how many poles and zeros that we have? Yes. How many poles? And how many zeros? See, here in denominator, we have,
Two,
yes, in
two, two zeros, madam.
two zeros. How two zeros?
Only one zeros. Two poles, madam.
Two poles, because s square is in denominator, right? So we have two poles. And if we talk about zeros, so do we have any s term in the numerator?
No,
No.
madam.
So we have zero zeros. Now, while discussing the transfer functions, I already mentioned that which was the only filter that would have that we can design as simple as just by using the poles. What was the filter that would have only poles and you can design the filter? Which filter was that?
Low pass filter.
Yes. So only poles, the filter that will be using only poles is the low pass filter itself. Other filters would need at least one zero, correct? So from here we can see that it is a low pass filter. Now, what other analysis that we can do? Let us put S equal to 0. S equal to 0 means low frequency. Okay? See, when we put S equal to 0, what we obtain is 0 plus omega c square plus alpha omega c 0, that is 1. Okay? So in low frequency, we are getting a gain of 1. Right? Now let's substitute S equal to infinity, which is high frequency. Right? So in high frequency, if I substitute high frequency or infinity, then what will I get my output as? 0, right? So now if I try to plot my frequency response versus gain, I know that in lower frequencies it gives me a gain of 1, at higher frequencies it gives me a gain of 0, then more or less it is a low pass filter, right? Am I right? And also,
Yes.
out of all 5 filters, this kind of behavior is only observed in the low pass filter. Now say, let's say you had some transfer function, okay? In lower frequencies, that is when you put s equal to 0 and s equal to infinite, in both the cases, say you got gain as 0, okay? If you got both the values same, that is either a constant value or 0, what does that mean? That it is neither a low pass filter nor a high pass filter. It is either a band pass filter or a band stop filter, right? Now, depending on, you would consider some center value, or say some pole, or some value, say get any constant value, and in that you see the transfer function, you compute the transfer function and find the magnitude of that transfer function. If that value comes larger than that of the extreme values, that is 0 and infinite, and if it comes above that, so let's say here you got this for s equal to 0 and this value is for s equal to infinite. You selected some frequency, say A. Okay. At that particular frequency, you are calculating your gain for the given transfer function. If that gain comes more than this, then it is a band pass filter. Okay. But if that gain comes out to be less than these extreme values, then it is a band stop filter. Okay. So here you don't have to calculate all the poles and zeros and plot the Bode plot to understand what type of filter behavior you are getting from a transfer function. Just by computing the behaviors at 2 extreme points, or 2 to maximum 3 points, you can define whether it is a low, which kind of filter it is. Is this clear?
Yes,
So this type of analysis comes handy when you have very complex circuits and or very complex transfer functions, very huge, very high powered transfer functions you have, say s to the power 5 with 5 factors or 6 factors, you have 6 order transfer function, 5 order transfer function. Now, sitting there and trying to get the factors out, factorizing the transfer functions, finding the poles and zeros, other than that, this is an easier way, right? Simply substituting, first of all, substitute 0 and infinite in S and simply see the values. If you get opposite values, that means it is definitely sure it is either a high pass filter or a low pass filter. Only the situation becomes a little tricky when both the values at 0 and infinite comes out to be same. Then you have to take another intermediate value, some value in intermediate, and you have to calculate the gain at that particular frequency, and then check whether it is higher than the extremities or lower than the extremities. Then you can clear cut get like whether it is a what kind of behavior that you will get. Now, what are the frequencies? Where are the cutoff frequencies? And all that is a different story. For that, you definitely need to work on like completely solving the transfer function and everything. But just for telling the behavior, you don't have to go through that much of pain. Okay, and it saves a lot of time also. And also, it helps you to cross check like whether you have done some mistake while analyzing or anything while deriving. All those mistakes can also be identified. So this is more of a trick Okay, it's a trick to cross-check yourself. Is this clear? So
Yes, madam.
all of
Yes.
you understood this problem, like how we are solving this, the approach towards this problem?
Yes, madam. Yes.
Okay. So let's move on to the next problem. So in this problem, see, it is given that you are given a system with 1 0 and 1 pole. It has a passband gain. What is the passband gain when the stop band gain is of minus 10 dBs? There are two conditions, that is WP is 5 times of WZ and B is WZ is 100 times of WP. So let me quickly draw my frequency response. So this is say for A, this is frequency response, or maybe I can write it directly in omega. So this is omega. Now say if my omega P is here, no, this is omega Z, right? If this is omega Z, then this is 5 times omega Z. This is 10 times omega Z. 10 times omega Z means 1 decade, right? And keep in mind that the Bode plots we were plotting were based on decade scale, right? So this is 1 decade. Okay. So here what is given is we have 1 0 at omega Z and 5 omega Z pe there is a pole, right? So somewhere the transfer function would start from somewhere, right? So let's say some constant value was there and it encounters a 0, right? So if it encounters a 0, and since it is a single 0, what should be the slope of my curve? It should increase by plus 20 dBs per decade, correct? Am I right? This is correct. So let's say if it was A and the slope would have gone on my curve, if it would have gone till here, then at this point, if I compute my gain, so if it would have not encountered any pole, anything, and my slope would have gone, like my curve would have gone increasing, at this point my gain would have been A plus 20, right? Now here it is already given that my stop gain is minus 10 dB. Definitely since my curve is increasing, so the lowest point is this point only. So this should be minus 10 dBs. So that means here the resultant would have been plus 10 dBs, right? But what is happening that at 5 omega z, it encounters a pole. So since it encounters a pole, the resultant would become like a constant, because plus 20 dB per decade slope, and because of the pole you would get minus 20 dB per decade slope. So that's why this becomes constant. So now this is my pass band. And what they are asking is, they're asking us to find the this passband gain, say X. So this is the gain that we need to find. Okay. So see, we know that in 1 decade, the gain that we observe because of 0 is plus 20 dB for 10 times, right? That is 20 log base 10 is 10, right? So now here if I want to find the passband gain, that is from minus 10, we will increase the gain by 20 log base 10. And what is the factor by which, where we have to calculate it? At 5 times. So this 10 times is this. Now because we are calculating it at 5 times, so that's why it would be 20 log base 10, 5. So this is, how much is this value? 20 log base 5 minus 10, how much is it? Yes, can somebody quickly calculate and tell me what is the value that you are getting? Minus 10 plus 20 log base 10, 5. Anyone? Okay, so the value that I am getting is 3.98 dBs. Okay, so the passband gain turns out to be 3.98 dBs. So here it is 3.98 dB. Okay, is this clear how we solved or approached the problem? Any doubts in the problem? No doubts, right? Okay, let's move to part B. In part B, it is said that WZ is 100 times of WP. So that means there is first a pole WP, then followed by a 0 WZ, that is actually 100 times WP. Okay, so here this is pole and this is 0. So that means some constant value would have been there, gain, and after it sees the pole, the gain will start to drop, and the gain will start dropping by a factor of, or the slope of, minus 20 dB per decade, and then it encounters a 0, it becomes flat. And it is given that this stop band, so this is stop band here, and it is given that the stop band gain is minus 10 dBs. Then you have to find this passband gain. Now here it is very easy, since we have come across 100 times. That means 2 decades. So simply by multiplying or adding 40 dBs, we will get this value. So this would be 30 dBs. If we move from right to left, If we are moving from right to left in the curve, then we can see the slope is of 20 dB per decade. So once you reach 20 dB, so once you reach the first decade, that is 10 times omega p, here you will be increasing the gain by 20 dBs, right? Because if here it was 10 dBs, then only at 100 omega p you would get a gain of minus 10 dBs, right? And now if here it was 10 dBs, again when you move a decade uh, upwards, it will again you will add a 20 dBs. So it is as simple as that. And mathematically, if you want to solve, there again we will be like 10 plus 20 log base 10 and 100. So here again it will be minus 10 plus 20 into 2, that is minus 10 plus 40, that is minus 30 dBs. Oh, sorry, plus 30 dBs. Is this clear? Passband gain. This is straightforward, right? Very easy. No complications, nothing. Is this clear to everyone?
Yes, yes, madam.
Yes, right? Okay. Now let's move on to the next problem. Okay. So in this problem, see, this is an active low pass filter. Why active low pass filter? Because we have an op-amp over here, which is an active component. So that's why this is again a low pass filter, but it is a active low pass filter. Also, this is not an ideal active low pass filter. Rather, it is a practical active low pass filter. So there is something called ideal low pass filter and practical low pass filter. Ideal low pass filters have certain issues because of which you go for practical low pass filters. And this extra resistor that you see, that has been added due for the uh, practical low pass filter. If it was an ideal low pass filter, you would only have one R and C with the op amp. Okay? So
Madam,
yeah. Yes.
hello, madam, can we call this as a modified integrator?
Yes. So the idea is, see, it is the same thing. When you call it a low pass filter or an integrator, what you basically mean is, in the flat pass band region or the flat band region, it is a low pass filter. Okay. But in the region where your slope is changing, in the transition region, in this particular frequency, it will behave as an integrator. So it's the same device, same circuit, everything remains same. It's just the operational frequency, like where you are operating your device, will define whether your circuit will behave as a low pass filter or will it behave as an integrator. Similar thing applies for differentiator and high pass filter as well. Am I clear?
Yes, madam, yes.
Yeah, so it is the same circuit only. It's just the operational frequency where you are operating your device. Depending on that, the behaviors will change. Okay? So, yeah. So, coming back to this problem. So, in this problem, in the low pass filter, as shown in this figure, for a cutoff frequency of 5 kilohertz, so it is given that FC is 5 kilohertz. What is the value of R2? You need to find the value of R2. So how to find the value of R2? So first of all, these two, capacitor and resistor, combined will give us the cutoff frequency or the pole that is required for the cutoff frequency. Okay. So if FC is 5 kilohertz, that means we know that cutoff frequency or a pole can be given by 1 upon 2 pi R into C. So here the R would be R2, right? So we have 5 kilohertz, that is equal to 1 upon 2 pi R2 into C, which is 10 nanofarad. So R2, the value would become 2 pi into 5 kilohertz into 10 nanofarad. So from here, what is the R2 that we are getting? After solving this, the value of R2 that we will get is 3.18 kilohertz. This is the value that we will get for R2. Is this clear? Any doubts in this? No doubts, right? It is simply straightforward. Like cutoff frequency is directly equal to 1 upon RC. Like omega is 1 upon RC. And if we are going for frequency, it is 1 upon 2 pi RC. It is as simple as that. Okay. Now moving on to the next problem. So see, in this problem, the circuit given below in the figure implements a filter between the input current and output voltage. Why it is said that you have to consider input current and output voltage? So basically the transfer function that you will form, your transfer function now would not be V out upon Vi, but rather it would be V out upon II, that is input current and output voltage. So that's the reason it has been mentioned that the filter has been implemented between input current and output voltage. Okay. And it is given that op-amp is ideal. So if op-amp is ideal, what is the behavior that we observe? If op-amp is ideal, we discuss this, right? First of all, there are no input currents. Second, we will see virtual ground concept, right? So here the voltage is similar to that of this terminal. So this here would be 0, right? So now, if I write KCL over here, so how would my KCL look like? I equal to I1 plus I2, correct? Am I right? So here I equal to I1 is V0 upon R1 plus V0 upon SL1. This is an inductor. So inductor ka when we write the impedance, we write it directly as SL. So this L transfers to SL, whereas C transfer to 1 upon SC. So this is basically the Laplace transform, how it transforms from one plane to another, nothing much. So here I equal to V0 1 by R1 plus 1 by SL1. What I want is V0 by I, right? So SL1 plus R1 by L1 R1S. So the transfer function actually becomes V0 by I is L1 R1S upon SL1 plus R1. Okay. So now this system has one pole and one zero. So out of these low pass, high pass, band stop filters, which filter you can design using a single pole and single zero? Yes. Which one was that? A single
High,
pole and single zero.
high pass filter.
High pass filter. Correct. So this particular filter that has been shown in the diagram is a high pass filter. How did we identify? We identified it based on this single pole single zero concept. If we want to analyze it, we can analyze it also. How we will do it? See, transfer function we know is L1 R1 S by S L1 plus R1. What I tell you is, let's take S common. So S by S, this is L1 R1 by L1 plus R1 by S, right? This S and this S cancelled. Why we did it, you will get to know in a minute. Now, in this reduced transfer function, substitute S equal to 0. The moment we substitute S equal to 0, denominator becomes infinite. And the whole transfer function goes to 0, right? But now, when you put S equal to infinite, this term, this particular term will go to, so this particular term will go to 0 when S equal to infinite. But the remaining term will remain as it is and the transfer function value will become R1. Now from this analysis also you can see for S equal to 0 transfer function is 0. For S equal to infinite transfer function gives you a certain value which is greater than 0. So definitely it is a high pass filter. So from there also we analyze that it is a high pass filter. Is this clear?
Yes, madam.
Yeah. So also one pole and 1 0 system. So it's a HPF. Okay. Right. Now moving on to the next problem. So in this problem, it says when frequency f equal to fc, that is the cutoff frequency in a high pass filter, for a RC op-amp based filter, then the gain obtained at that particular frequency is how much? So what is the value that you would get for a high pass filter when we substitute a cutoff frequency at the place of the frequency analysis? So for this, one thing that we have to always keep in mind, and it is almost universal, is when we have a single pole system or single order system, at that time, at the cutoff frequency FC, okay, at FC, there are few things that happen. First of all, power becomes half. That's why that cutoff frequency point is also known as half power point. Okay? And we call it 3 dB point, right? Why? Where does that 3 dB comes from? Minus 3 dB point. So that 3 dB comes from, since the power is half, so what is power? It is either P equal to I square R or P equal to V square by R, correct? So if the power is half, that means considering that the resistor values are constant, what will be the effect on voltage or current? They will be root 2 times, right? So here actually what happens is the gain becomes 1 by root 2 times. So at FC, the power becomes half. The gain value, exact gain value becomes 1 by root 2 times. So whatever is the DC gain, if you want to calculate the exact gain value, it will become 1 by root 2 times. And in dB scale, the gain becomes minus 3 dBs of DC gain. Because when you go for log of 1 by root 2, you will get this minus 3 dB value. So 20 log root 2 gives you 3 dBs. So from there you get this value of 3 dB. So it is 1 by root 2 times. So for a single order system, when there is one pole that you encounter, the slope becomes minus 3 dB or plus 3 dB, depending on whether it is a pole or a zero. And if we are talking about the actual value, so actual value is the gain becomes 1 by root 2 times. Okay? And if we talk about this 1 by root 2 in decimal value, it is 0.707. So the gain becomes 0.707 times. This is true for all the single, like whenever you encounter a single pole or a single zero in a Bode plot or in any frequency response, this effect you will always see. Like compared to a DC gain or a constant gain, which was already there, after that, when you encounter one pole or one zero, your gain and power values change accordingly. Am I clear?
Yes, madam. Yes.
So this maybe you can keep in mind. So that is the same thing. So when we say minus 3 dB, if you look into the derivations of where this minus 3 dB value is coming from, it comes from the same analysis. Okay. So yeah, let's move on to the next problem. Okay, so this is about normalized transfer function. So where do the poles of the transfer function of normalized low pass Butterworth filter exist? See, Butterworth filters, so what we discussed are low pass, high pass, band stop, and all pass filter. These are types of filters, right? Now, these filters have been designed by different scientists in a different way, in different ways with different purposes. Okay, so let me give you an example. For example, as I mentioned earlier, that for low pass filter to make it ideal, we need to increase the order of the filter, right? I said that, correct? If you remember, I mentioned that we need to increase the order of the filter. But what happens is when you increase the order of the filter, so when there is a single pole, I mentioned the dip that you obtain is minus 3 dBs. Okay. When you have two poles, the order, so the slope becomes steeper, but the dip also increases. It becomes minus 6 dBs. Right? When you have a third order filter, the slope will be further steeper, but again the dip that you will observe is minus 9 dBs. So what is happening that at that particular point of XC, that is the cutoff point where you have your poles, as you start increasing the number of poles in order to increase the steepness of your curve, what happens is you start losing the gain at that particular frequency or at that cutoff frequency. Now, see, if you want to retain that frequency, like gain at that particular frequency, and you don't want to go much, like you don't want to deteriorate your gain at the cutoff frequency, and you maximum want the deterioration to be minus 3 dB. No matter how many orders you increase, no matter how many orders or how many orders of filter you increase, but the deterioration of your gain at that cutoff frequency is minus 3 dB. I'm specifying this, that is at minus 3 dB. So that particular design was given by this. So that particular design can be obtained by Butterworth filters. So sorry, in Butterworth filters, what happens is no matter how many orders of filter you go for, the dip or the uh, deterioration at FC is only minus 3 dBs. Even if you go for 10th order or 12th order of filters, then also the dip is only minus 3 dBs. So that is the advantage that you get from Butterworth filter, right? Likewise, there are different types of filters, different topologies of filters that people have come up with, like the researchers have come up with. They have certain advantages, definitely. So that's why there are different various types of filters. And one of them, which is, I believe, which is most celebrated, is Butterworth filters, given the advantage that it only deteriorates by 3 dBs. So which is the advantage, and it's a huge advantage for us. So that's why we study Butterworth filters a lot. In Butterworth filters, there is a certain table that must be followed, and you have to design your so the transfer functions are fixed in Butterworth filter. Now you have to use the components such that those components will fit in the transfer functions. That's how Butterworth filters are designed. Okay. So anyways, if it is a normalized low pass Butterworth filter, where do the poles of the transfer function lie on? So if it is a normalized Butterworth filter, then all the poles lie on the unit circle. Okay. If all the poles will lie on the unit circle. So if I talk about a normalized Butterworth filters transfer function, the transfer function looks like this: 1 upon 1 plus s by j 2 to the power n, where when we look for pole value, that means 1 plus s by j equal to or equal to 0, then okay, this is 2 to the power n, so s equal to minus 1 to the power 1 by 2n times j. So this is basically, here will come out to be e to the power j by 2k plus 1 by 2n e to the power j omega by 2, where k can take integer values. So 0, 1, 2, so on. So here the poles will lie on the circle with unit radius. So this is basically what is meant by normalized Butterworth low pass filter. Since it is normalized, that's why its pole will lie on the unit circle. This only idea. Yeah, moving on to the next problem. Okay, do you people have time? Should I take the problems now, or do you want to continue them next time? Whichever way you feel like. Should we continue or stop here and continue the problems? Continue with the problems in the next session.
Madam, next session.
Okay,
Next.
maybe we can do one thing. Just finish this problem. So in this problem, again, we are going for analytical analysis. Okay,
Okay. Okay.
and then we can stop. So see here again, whether it is a low pass filter or high pass filter, how would you define? So first of all, low pass filtering for low frequencies S equal to 0, capacitor is open circuit or short circuit for low frequencies? Yes. For low frequency, is the capacitor open circuit or short circuit? For low frequencies, it is open circuit, right? So if the capacitors are open circuited, then nothing is passing from here to the output, right? And no current flows inside your op amp. So that means whatever is V in, that V in will apply here, and V out becomes V in, right? So this is what is happening in low frequency. Now when it is high frequency, now if it is a high frequency system, then what will happen? S equal to infinity, and capacitors are short circuited, correct? So if capacitors are short circuited, that means, see, first of all, your Vin here, if it is R and this is connected to ground, that means Vin becomes Vin by 2 at this point. And that is being fed to here V out, and here it is 0. So from here, we can clearly see that at this point, your output is 0. And through virtual ground concept or virtual short concept, at this point also, this point is connected to ground. Here it is 0. Here it is also 0. So V out is also 0. So V out becomes 0. Now at high frequencies, if it goes to 0, the signal goes to 0, and at low frequencies, the signal is V out equal to V in. What type of filter it is? In low frequency, you are getting an output. In high frequencies, your output
Low
goes
pass
to
filter.
0.
Low
It's a
pass
low
filter.
pass filter. Yes. So it is a low pass filter. So that's how we analyze the circuit without doing any calculations.
And madam, it is second order because two RC sections are there.
Yes. Definitely it's a second order filter. And if you want, what you can do is you can find the transfer functions also. Like using the capacitors, why don't you people try and calculate the transfer function? And you would see that since it is a low pass filter, you will get a denominator with S square factor. And definitely you would not get any 0, because we have seen that in low pass filter we don't need a 0, right, for designing. Or else if there is a 0, then that 0 also would be like away from your poles, like both the poles, it would be away from both the poles. So maybe you can calculate this and see, but since R and C values are not given, so but
Madam, this circuit is having gain 1 unity. Is it a voltage follower circuit?
gain 1, so in low pass, right? So when we have gain 1, so that means if we draw our frequency response, so that means you will like the gain profile for the frequency response will start from 0 dB. That is the only information that you can get from here.
Okay.
Yeah, it's not voltage follower, but definitely at low frequencies, since V out and V in are coming to be equal, then we can say it is a voltage follower, but it's not exactly the voltage follower, right?
Okay, madam. Thank you. Thank you.
Yeah. Any other doubts? So maybe we can break over here. I had few 2-3 problems. We can take up them next time, and we'll also learn about some new concepts next time. Okay. If you have any doubts, feel free to ask. Else we can end the session over here and meet next time. That's all from my side.
Thank you, madam.
Thank you. Thank you for joining.
Ma'am,
Yes.
actually, I had like my summons going on, so it just got over today,
Okay.
and I couldn't really keep up with a few modules in between because I had to focus on the exams. So
Okay.
I think I will sit and do all of that in this week. So if I have any doubts with the previous modules, can I please get it clarified in the next class?
Yeah, you can go through the lectures and notes. You already have access to them, right? YouTube
Yeah,
lecture links and notes. Yeah, you can
yes,
go through them. And
yes,
if you have any doubts, you can feel free. So you can either join me early because I start at 6:05 waiting for other students. So meanwhile, in that 5-10 minutes, like I join by around 5:50. If delayed, it will be by 5:55. So
okay.
5:55 till 6:05, you have the 10 minutes domain, or
Yeah.
else you can sit after the class also. That is also fine for me.
Ma'am, is there any way I can contact you like other than only on this meet?
You can contact me on this meet so we can have one-on-one interaction. Other than that, my email has already been mentioned. So you can email me, like if you have some urgent doubt and want it to be clarified urgently, you can email me also. I'm available.
It's just that I'm like in my first sem, so I'm not really able to keep up with every concept that
Okay.
fast. So I'm struggling a little bit. That's why I wanted your help.
Okay. No, I'm available on email, so you can email me. But I have not taken any difficult concepts. I've tried to go for easier concepts only. Uh,
Okay.
so yeah, maybe you can follow through the lectures and the notes. And
Yes,
if you
ma'am.
have any doubts, you can ping me. Also, while watching YouTube video and you feel there is some doubt, you can ping me in YouTube also. So I can reply to your doubts there as well. No worries.
You have your own YouTube channel?
Yes, I do.
Oh, I did not know that. Where
Oh,
can
so
I
all
access?
these lectures that I'm taking, they are
Huh?
being recorded simultaneously and I immediately upload them on YouTube. So, are you taking this NPTEL course? Do you have access to the links? No?
Yeah, I do, but I did not know that you have your own. I'm just looking at the lecture videos, not your solving session videos.
Oh no, solving session. I was talking about solving session videos. So all the problems that I solve and the like concepts that I am teaching, all
Okay.
these are being recorded from the beginning till end, and you will get that on YouTube. So you can simply search my name, D Sharda Devi,
Okay.
and yeah, you'll get my like picture also for the easy access. I have put up my picture also, and
Okay.
there you can go through the module. So this is analog circuits. So I have different playlists, but for this particular course you can go through the analog circuits playlist. It has all the lectures. So this is sixth week, so
Okay.
you will get all six lectures within half an hour. I'll upload this lecture as well, and
Okay.
you'll have access to all of them.
Yes, ma'am. I'll just go through all of it in this
Yeah,
week.
yeah. And maybe you can subscribe also, so you'll get notifications and all as well. Because we
Sure.
have four more lectures, 3 or 4 more lectures.
Okay.
Yeah, you can go through them. Oh, I didn't know you don't know about this. So all these lectures are there on YouTube, like my solving
Okay.
session. So even if you miss the solving session, then also you can go through the problems.
Yeah, I wasn't able to attend last few weeks. That's why I
Oh,
was a little
okay.
scared. Yeah.
Yeah, you can go through them on YouTube.
Yes, ma'am. I'll do that. Thank you so much.
Okay. Yeah, thank you. Thank you for joining.
Yeah.
Deshmukh ji, any doubts?
No, madam. No, madam. Thank you very much. Thank you.
Oh, okay. Thank you, sir. Thank you for joining. So if
Thank,
no doubts, maybe we can end over here and meet next week.
thank you, madam, very much.
Thank you. Thank you.